Okay, everyone, welcome to TAMIDS Scientific Machine Learning Lab workshop. And this is our second one. And we had our first one already posted. We have all the slides and also the GPU notebooks and the recorded video clips posted on our website. So this one is, on my side, it's almost identical. But I believe Levi might have something new to show you all. I just put a lot of burden on Levi for the hands-on sessions. So there will be 3 parts for this workshop. The part 1 will be a very short introduction to scientific machine learning. And part 2 will be some a short introduction to TensorDiffEq. And part 3, let me see if I can remove my tile here, drag them down to the bottom. Part 3 will be a hands-on session. So we'll have about half an hour to talk about scientific machine learning and half an hour about the basics of TensorDiffEq. And then for the final hour of the workshop, we'll be going through the GPU notebooks and get you all started. There will be a 5-minute break in between. So for scientific machine learning, I'll definitely refer you all to these 3 resources, links that you can get to some background about scientific machine learning. It's not something brand new, but the title and also probably the subject itself has been there in the community. People have been doing similar research for decades. But it's just like a new brand for a lot of things put together, and we give it a new name. It's similar to data science. People have been doing statistical machine learning, statistical analysis, and for many years. And then, after the rapid development in computing technologies and also algorithms, data science itself popping up as an emerging field. The same goes for scientific machine learning. We are expecting a lot of new research and educational effort along this line in the near future, and hopefully you all could get started along this line, as soon as possible, and start picking up some momentum when the new field just gets started. So the main connection between machine learning and scientific computing is in the model training itself. So when you're trying to do the model training, if you are familiar with the traditional scientific computing methods, you're starting with governing equations, and you have some data prepared, collected from your experiments. And you have some governing equations derived by some mathematical physicist or some people that have been doing this for years, and they publish papers, and then you learn from textbooks. And you took those and consider those are prior knowledge about a particular field, and then you code it up in your computer if the equation is too hard to solve analytically, and then you have a program, and we usually call it a model or a simulation code, and you can make predictions. That's how you do the traditional modeling. I would say it's numerical simulation, but traditional in a sense, it's traditional in the computer era when you have computers and to do all these numerical simulations. But there's another paradigm that people have been following lately. Basically, we are not relying on the scientific model anymore. We just say, okay, we have some data, and we know there are some mathematical theories can telling me that there is some sort of special structure people call neural network can help me to approximate my theory in some way. So whenever I give it an input, I'll get some output. So with the sample data and this mathematical structure, let's just call it, neural network for now. It could be called something else. Just consider it's a mathematical structure. And with that, you can put that into your computer. And fortunately, with this mathematical structure, with all the systematic way of dealing with those, it's relatively easy to code it up, and you can plug in your data and use someone else's code, and you can construct your network yourself. But just consider you are just taking someone else's code with your own data. You can start just working on the model, and long after you train it for a while, you get your model ready. And you can plug in your new data set, and you put in your computer, you can make predictions. So now the main difference is that with your mathematical model here, your network model here, you don't need to worry anything about your background knowledge about the particular equations or governing equations. All you need to know is that these data sets are relevant to your research, and there's some expected output you want to target, and you plug in your network, and it'll give you output. It sounds like a dream comes true, but it seems to be the trend nowadays for a lot of research areas. People take the data and take this mathematical structure and create a function, and makes the whole life easier for them. So that's basically two paradigms for doing research using computers nowadays. But of course, I simplify a lot of key factors and key concepts in this on this slide. But I think I convey the idea that you have multiple ways of doing things. At least the two ways of doing things. Now, in addition to the mathematical governing equations and also the mathematical structure, another key factor plays into this balance is the data. So the amount of data you have more or less determines the method you want to use. Traditionally, think about several hundred years ago when the data connection was relatively harder compared to now, and there were not so many digital equipment for people to easily grab some data. Even to take an image, now you just push the button and take the snapshot, right? You can just you can take an image and you can convey a lot of information with that one single image. But back then, even for that, you needed someone with good at drawing and give you some sketches. And for those who have been trained to do that, it's relatively easy, and they can do that. Probably give them 10 or 15 minutes. For those who are not familiar with the old techniques, they have to learn how to getting all the information recorded and conveyed. So that's the amount of energy and resources needed to just get the data. And so collecting data and cleaning the data, it's not an easy task. Even nowadays, if you really want to get some high quality work done, collect and clean data, it's still taking a lot of your time. So for this, that's back then several hundred years ago, when I'm talking about human beings as a whole, we didn't have much data to deal with, and we had to be smart. So that's why there are a lot of mathematical theories there just to simplify the way how we describe our nature, describe how the universe works. And that's probably the main driving force, because you have to be smart to really start making predictions. And those are the starting point for the theory-driven model. But nowadays, with more and more neural networks and some other machine learning models there, people are getting lazier in the sense that we just rely on all these mathematical structures and help us to predict what we need. And in some sense, we just treat whatever we do as a function. And no matter if you're working on very, very mathematical structure based on your governing equation, or you're working on some empirical formula based on your data, and we are constructing kind of equation or function for us to make predictions anyway. Now with the data-driven model, we are just directly targeting the function itself. There'll be less and less thinking along the theory-driven direction that if you're familiar with, if you take any courses in physics and chemistry, and even biology, sometimes you need some theories behind it for you to create some theoretical models and for you to derive something. But with more and more data, there'll be less and less theory, And the data as you are collecting, might be noisy, but the problem is this method is getting actually realistic. For a lot of theory-driven models, one major problem is the realistic of the equation itself. In most cases, you simplify your equation in a certain way, you get rid of all the viscosity, friction, you think about some ideal cases to come up with a very beautiful mathematical equation. But in many cases, it doesn't really work very well. You have to consider a lot of parameters in your equations, and you need to do a lot of tuning to, in realistic cases to make that work for you, or you need to consider many other factors which might not be considered in the original model. So, there's a back and forth with these two, but the last thing I think is, which is very, very important for us to understand that the data-driven model, especially deep neural network, it's more or less like a black box in most cases. We understand those mathematical terms, but we don't understand what they work together to give us the final function. How they can, tell an image if it's a dog or if it's a cat. And there might be some, high-level abstraction that we don't understand to get this neural network working, deep neural network working. So that's the major shortcomings for one of the major shortcomings for deep neural network. It's a black box. It's hard to interpret. And that's also one of the major reasons why it's not used in some other fields that we needed people to explain why it's working. And series-driven model is still widely used, mainly because it's explainable. Now, the question is, can we do something about it? So there have been a lot of work doing so-called data assimilation. If you are doing climate modeling, weather forecasting, you probably have heard about data assimilation a lot. Common filters, and those are from ocean engineering folks that are doing this ocean simulation. They want to inject the real measurement data into the model, so then they can get a more accurate model for making predictions. And that's how the data assimilation goes into the picture. But again, the data assimilation itself, it's more or less like a technique, trying to unify the observational data and integrate operational data and a theoretical model. But there's another way out, and that's exactly what we'll be talking about, the scientific machine learning. Even though we are mostly scientific machine learning is more focused on machine learning side at this point. The scientific side, it's still ongoing and people are still working on that, but we are trying to connect series with machine learning models so that we can get better results when we are making predictions. So I just want to show you one slide about the, I'm not sure it's, not sure if, I'm sorry, I'll mute some of the attendees just in case I heard some echoes here. I'm sorry about it. So I have one slide here just prepared for you all, just to have a rough understanding about what a data assimilation is. So, at a very, very high level, you can consider it's like a mixed usage of simulation and observational data. So just look at the one to the left here, top left one diagram. So you start with a simulation. That's a blue curve here. And then at some point, because your model itself might not be very realistic, you made a lot of assumptions, and in your model, when you're building your model, there are some systematic errors, or even when you're doing numerical simulation, there are some numerical errors accumulated. So your solution might be shifted from your original solution space to some other, whatever manifold hyperspace somewhere, which are completely non-physical. So one way to drag them back into your solution space is just to inject some observational data, and by more or less like a weighted average between the observation and your simulated results, you can pull your results back to some point, which might not be exactly the the physical solution for your problem, but it's getting closer and closer to the observational data, which is when you are doing science, whatever you see, you observe, you measure, are the data points you need to connect to. You want to you want your model to be able to predict the reality instead of you tweak your observation data to fit your model. That's not the way how we do science. So we always rely on the ground truth that we observe. And we try to modify our model to meet the what we observe. Right? That's how we do science anyway. So the basic idea is that we use the data points we observe as the like a spring force. When you're further away from a spring, the spring will pull you back, like a Hooke's law, right? So the data will try to pull you back to your solution space. And you can continue doing this after, probably when you're doing simulation for, say, 1 day weather forecasting, you can do this every 15 minutes or half an hour, depending on how much observation data you have and how often you want to do that. There are a lot of operational and practical reasons that you want to choose different compilation schemes, integration schemes for data observed and for data simulated. So that's one way to do it. There are, of course, there are many other ways. You can continue your simulation, but you directly inject your model or inject your observational data in your model so that your model could be parameterized based on the observational data. And then you continue your simulation without doing this massaging of data between observational and simulation. So there are multiple ways of doing that. And I have a link here. If you have access to the slides, you can go there to NCAR, which has been, that's a place where a lot of simulation like this have been done. And so that's data simulation, which could be considered as some early stage prototype for scientific machine learning in some way, even though it's not directly doing machine learning, and it's trying to merge and trying to integrate observational data and the theory together. It's just another paradigm with, I think it's always to try to get the observation and your theory working together. So for scientific learning, you can consider it's like the best of two worlds, but as I just mentioned, current research is mostly focusing on machine learning side. We're trying to just get the model up and running and give us best result, but how the physics got injected into the model building, it's not very, very elegant at this point. But we have been trying to do that, and also our laboratory, it's also deeply involved in doing this ourselves. So think about I'll show 3 scenarios that how deep neural network model and a series-driven model can work together. Series-driven model considers a governing equation. So you have physics, you have all the equations you want your result, your solution to satisfy. So the first scenario is so-called a feeding kind of paradigm, more or less like you have some series-driven model already set up. It's well tested, and you just want different scenarios, and you want to generate different scenarios that can fit into your model. This is usually used for parameter search, for drug discovery, and also. So you have a different, you have a neural network to help you to generate, to populate your solution space, and you want your model to search inside the solution space where to get the to have the particular cases and match your requirements very well. So of course, this will be not just a one serial, this will be a loop. So you output from your series-driven model here, will be going back to your feeding, your generating. Let me see if I have my annotation. So there should be a loop here that will help you to get some feedback from your series-driven model back to your generator. So your generator can know exactly, not exactly, but roughly, statistically, how can I say it's you can have a weight or like a weighted generator, so it knows what are the most suitable candidates that be more interesting to the target I want to look for. So that's a feeding scheme. So you use a neural network to help you, more or less like a random number generator. But this random number generator has special statistical properties that can be controlled by the output from your series-driven model. I hope that's clear. And then there's another one. I'm sorry, let me try this. So there's another paradigm, which is in the center here. It's called surrogate model. So basically, you have your theory-driven model. It's you have a lot of FEM and fine difference code or fine element code, and to help you do the simulation. And you want your network to help you to post-process your data. And what you do is just dump all the data output from your simulation and use neural net to either extract the patterns from your data, or you want to completely replace your traditional high-def, high-fidelity simulation model, numerical model with this neural network. So since you already have the theory-driven model, you can take input and give you some output. You can use your theory-driven model to create data sets for your neural network, to train your neural network. So by doing that, you can train your neural network to replace original theory-driven model. So that's called surrogating. The pronunciation might not be, the pronunciation might be wrong, but that's another way of using your network to help you doing your science. It's called surrogating. And the last one that might be more and more interesting because it seems to be called nesting. This nesting method seems to be one of the most flexible way to mix for researchers to mix theory-driven model and machine learning model. Basically, what you do, you just treat your neural network as a function itself. Instead of solving the whole problem, you target a very specific area, very specific equation in your big system, and then you use the data generated in your traditional theory-driven model, and use that to train your network and replace part of it. So you just simply use this machine learning model as a function to replace part of the function you already have. After you train it, your network's more or less like a function. Replace it, it just works like before. It's just more or less like doing plastic surgery, right? You replace your body part with the plastic components, and in the future, I think more and more people will be relying on this kind of surgery physically. But it's in the same idea for neural networks. When you want to just simply replace the traditional traditional solver for a certain type of equation, you can simply replace it. I believe more and more neural network will be created and released, by a community to solve very specific problems. And this will be helpful for you to build up your own system quickly, without you to spending a lot of time to getting your model trained, etc. So I hope more and more solvers will be popping up like this, so you can build up your systems quickly. So for traditionally, you start with your physical problem. At the very top, you make observations and you build up your models. If you're already familiar with your field, you know which equation to use. And then you do the discretization, and then you write down either C code or Fortran code or Python code. They do convergence test, and you compare that to some analytic solution with some simple problem, toy problems, and then you apply your numeric code to the realistic problems you want to study. And that's basically how the traditional numerical model system is working. That's more or less like a workflow you want to go through. And I'm just here referring to my own experience with finite difference. If you are doing finite element, spectrum method, and even Monte Carlo simulation, you are doing something that's kind of similar, even though you probably don't need to worry about convergence and discretization and other problems. But again, the basic workflow is more or less like this. But for data-driven model, you have data, you have machine learning algorithm, just for example, the neural network structure. That's all you need. And you get the data, get your network, you train your model, and then test it. If the model gives you result with a certain accuracy that satisfies your requirements for your application, you're done there. If it's not, then you probably need to collect more data, adjust your neural network structure, and do more training, and until you reach the final model that can give you more accurate output. So the neural network has a biological inspiration from neural science, and in the sense that all the neurons, as they are connected, they are sending signals from one to the other, and there is some activation. If certain signal if a neuron is activated, it will send the electric signal to the next neuron, and then so on and so forth. So you can go from all the way from the input to output, all the way from your perception. When you touch something, your brain knows something, you'll have some reaction back. Your muscle, you do something. So neural network is more or less like you have multiple layers of neurons connecting to each other. Here I'm just showing you a so-called dense layer, which actually used a lot in scientific machine learning area, but for most of the computer vision and other methods are using more complicated structures. But dense layers seem to be working fine so far, and people have been trying different structures in scientific machine learning to explore the features of the regional physical space in the real problem. And for the neural network itself, you can consider for each layer, it's more or less like a weighted average. But at the end of every layer, you have a so-called antivirus function, which will give you the linearity to map your first layer to the neuron to the next layer. You can do this, continuous doing this until you reach the output. So it's like a nested weighted function with activation function in between. So all the things, all the parameters and all the biases that we want to, all the weights and biases, which are called parameters we want to extract from this training process, there are the unknowns. So you have your input, you know your output, and you want to train your model to figure out all the weights and biases. So then your input and output could be matched well with your ground truths. So activation function itself is a nonlinear function, but if you just look at one of them, like a ReLU and a leaky ReLU, these are the two widely used activation function. They are very simple, but this if the derivative of the non-continuity of the derivative of the ReLU gives you the nonlinearity in your final neural network. That's a very surprising but interesting thing to notice. If you look, usually, when the neural network just got started, a lot of people are using complicated nonlinear functions just to introduce more nonlinearity into the model. But it turns out they are getting really expensive to compute, and also they are not giving very good results compared to the even simpler ones. So it turns out almost everyone's using ReLU and a leaky ReLU in their model as their activation function for building up your network. There are some other new ones recommended, but if you go to any literature and also online articles, you can see almost everyone's using ReLU or leaky ReLU nowadays. So to train a model, you need to define some loss function. This loss function, if you are familiar with the physics, there's an action. You can define an action, and then you use a least actions principle. You can derive all your mathematical, all your physical laws. That, as long as your action itself is well defined. And here, this loss function actually controls a lot of things we'll be dealing with the neural network. And a good definition of this loss function could help you to not only minimize the error, but also put a lot of constraints in a solution space that you want to explore. And to find the ways and biases that can minimize your loss, people are using so-called the backward propagation method, and they take the gradient of the loss function against the weights, and then put an extra parameter alpha, which is the learning rate, and that will control how far you want to go for every iteration, and also minus sign more or less gives you the direction about how you want to change your weights and biases. So this this kind of method will help you to get to the minimum quickly, depending on how big your alpha is and how are the parameters you want to put into this training process. So all these parameters are called so-called hyperparameters. Those are are the most tricky part. When you train your neural network, you need to play with all this on a daily basis. You need to figure out, the best combination of all these hyperparameters, give you the best results, and minimize your training cost. So today we are not going to go into details about how to train your model, but the basic idea actually is very simple. If you're using some deep learning frameworks like a TensorFlow or Python, they have built-in functions for you to do all this quickly. So to summarize, I think we can consider deep neural network as a universal approximator, and this has been proved to rigorously by some people, mathematicians, not so many years ago. Of course, when I started for the proof itself, it's mostly focusing on very simple neural network. They are using so-called multi-layer perceptron, just the dense layer I just showed you. They are not using fancy convolution neural network and some other neural networks. And also they are mostly focusing on simple, smooth functions. But it turns out it's actually possible to approximate almost any function that known so far with deep neural network. And as long as you have enough neurons to resolve the fine features you want to resolve. And that's the approximator part. And on the other side, Pinker's theorem tells us that not only the numerical, the values could be approximated, but also the derivatives could be approximated at the same time. So that's very important in the sense that when you're doing scientific machine learning, you are dealing with the derivatives a lot. because almost all the physical laws that described with a part of different equations, they're mostly concerned about derivatives and the same derivatives. Sometimes we see high order derivatives. Being able to approximate not only the value but also derivatives can give you a better description about the connectivity, spatial connections and correlations, that might not be easily resolved by just fitting the numerical values themselves. So that's, I think, one of the main reasons why it's feasible to use a deep neural network to approximate functions and to solve PDEs. So this is a very simple diagram. I'm just showing you, all I want to say here, you can just treat a deep neural network in the same way when you're treating other functions. You can call it any way you want. You can arrange it any way you want in your solver, your pipeline. And to train your neural network, all you need to do is just figure out a good loss function and then put it into the deep learning framework and let the computer to handle the rest for you. But again, it's not, of course, not as easy as you will see in Levi's talk with the TensorDiffEq, and there are a lot of work going on to make all the user interface easier for you to get started. If you're not familiar with the programming, at the very beginning, this might be scary to get started, but learning to use high-level programming languages like Python and even like libraries like TensorFlow and Keras, and also TensorDiffEq, all the library will be helpful for you to get started quickly. And I will not cover this automatic differentiation, and this is just building mechanisms into for TensorFlow and Python, or those kind of deep learning frameworks. And just consider it's a free way for you to calculate the difference. Differentiation of your functions, at a very high accuracy. I think there are no loss here, no numerical loss when you're doing this, which is a dramatic difference from a way when you're doing finite difference and the finite elements method, using that method. So lastly, I just show you the diagram, which will be closely relevant to the paradigms that TensorDiffEq is following. Basically, we are trying to solve PDEs, and we are constructing all the loss functions with some sample nodes together with certain physical regulations like a boundary condition, initial condition, etc. And then we train our model to minimize the loss. And in the next half an hour, and Levi will give you a quicker overview about TensorDiffEq, and then for the next hour, we are going to some examples, and Levi will guide you all through some examples, and we'll learn how to use TensorDiffEq to solve equations, different kind of equations. And with that said, now it's your turn, Levi, and I'll hand over the microphone. Oh, any questions? I'm sorry for the delay. I think it's probably 10 minutes more than I was supposed to talk, but any questions so far? Okay, good. You are super. You know everything. So I'll just shut up and let Levi to show you all what TensorDiffEq can do.
Yeah, absolutely. All right, let me see if I can share real quick. Let's go ahead and share my whole screen here. All right, great. So thanks, Dr. Tao. Appreciate the introduction and going over some of the sort of mathematical and machine learning primitives sort of required to more or less understand what is happening under the hood with TensorDiffEq. And this is built on top of TensorFlow. We're going to kind of get into the slides a little bit, but a high-level overview of TensorDiffEq is that it is a Python package built on top of TensorFlow, designed to train both forward and inverse models of partial differential equations and systems of partial differential equations using some scientific machine learning methodologies, mostly the physics-informed neural network framework for those that are kind of researching this space and sort of know that there's, you know, a few different ways of kind of going about scientific machine learning and how to solve forward problems using machine learning algorithms, solve inverse problems using machine learning algorithms. So some of them require you to backpropagate through a solver. Some of them just allow you to kind of do a physics constrained optimization. And so in this case, TensorDiffEq does the latter, and we'll kind of get into what that means here shortly. So forgive me, to start off, my name is Levi McClenny. I'm currently a PhD student in the Department of Electrical Engineering, working with Dr. Ulysses Braganetto. We've been working in the scientific machine learning space for a little over a year now. Since then, have a few publications, preprints, as well as some software in the space. And so we're going to kind of cover some of those things today. So with that, we'll get it going here. So this is a high-level overview just of the package, and we'll talk a little bit about the software here, where TensorDiffEq fits into the current landscape of different physics-informed neural networks, as well as other scientific machine learning solvers. And then we'll, I think, do a brief break, if I remember correctly, in the agenda, and then we'll get into some Jupyter notebooks, Colab notebooks that actually execute the code, and you can kind of see and step through it for yourself. So with that, we'll get it started here. If I can get to the next slide. All right, great. So the motivation for TensorDiffEq is that for the most part, current PIN PDE solvers, especially like open source solvers that you don't have to request access to, or aren't sponsored by large organizations, are typically limited to single GPU implementations. And also existing software is primarily, or existing TensorFlow software is primarily based in TensorFlow 1, while definitely a very capable framework. There's a lot of optimizations that the team at Google is working on really diligently to make the newest generation of TensorFlow that came out in, I believe, 2018, TensorFlow 2, making it faster, more optimized to perform things like automatic differentiation faster, building out some optimizations that occur inside of a neural network. So there's a lot of great advancements going on, more or less by the Google team, that are being rolled into TensorFlow 2 that can be taken advantage of if you use that framework. And so whenever you build out some of these software packages, depending on which ones you use, the way to actually build out a partial differential equation, way to define your problem, is a little convoluted. It's a little tough to kind of get to the bottom of, like, okay, what am I actually trying to do here? And basically what I set out to do is generate a package that allows you to just define your weak form PDE or strong form PDE. Define a residual function that you need to drive to zero, which is essentially kind of at the crux of all numerical method solvers, right? We have a residual function, we're trying to drive that to zero, and typically that function is defined in terms of its partial derivatives. That's kind of how we get to a solution network that we'll discuss here in a bit. That's how you get to a solution. And so I wanted it to more or less read like you're defining a PDE in plain English. You're just writing out the equation. This is what I want to solve. And so we'll get into how that looks here shortly. A lot of that's taking advantage of some of the things in Python. taking advantage of some of the things in TensorFlow so that we can actually just kind of define it that way. But that's really what I wanted to do, is build a wrapper around this so that you could kind of interface with it a little easier than some of the current software that's floating around out there. And then the other thing too that's unique about TensorDiffEq that I spent a lot of time working on is being able to make it capable of solving on a multi-GPU system. And so I've tried it up to scaling up to 4 GPUs and in the process of working with the Grace, the new HPC Center Grace, to scale it a little higher than that. Currently, you can scale across, a single node, multiple GPUs. There's no scaling across multiple nodes right now, for those that know the distributed computing kind of frameworks and how you can kind of distribute across different GPUs and different processors and that sort of thing. So currently it's limited to a single node multi-GPU, but you can stream up, and I've solved problems with millions of co-location points. And the weak scaling is pretty good with TensorDiffEq. There are papers that have come out that, there's all sorts of optimizations that are happening in the space. But so far it's, more GPUs equals more computation, more, residual points per second. How that exactly breaks down is a little bit different. There is a point of diminishing returns there where your problem is so small that scaling it across multiple GPUs actually doesn't help, because it just makes things more complex as things communicate across different, wires, and it slows things down. Sometimes there's a problem where you want to have it on one GPU, so there's a lot of nuances there that we're not going to really cover today. But this package is capable of scaling across multiple GPUs. So the implementation that we built, like I said, is capable of multi-GPU training of large or high dimensional domains. So the main reason why we wanted to be able to scale across multiple GPUs is because once you get into 3-dimensional problems or higher, 3 dimensions with time, that sort of thing, you need a little bit more horsepower to be able to train on all of the different possible combinations of the different inputs to your domain. So whenever you train this, you train across all possible combinations of X, Y, Z, and T, let's say, that are in your domain. So whenever you do that and you want to be able to calculate different points all inside of that domain, there's a whole lot of points that you have to work with. And so the premise of this was that we want to be able to scale that. We wanted to be able to distribute that. And so that's what we built here. And the TensorFlow 2 implementation, like I was saying earlier, there's a lot with that. It includes XLA optimizations, grappler, graph mode optimizations. LLVM and MLAR kind of allow you to scale across different types of computing platforms. So it's kind of like a little bit, it is optimized specifically for hardware. So it's a feature of TensorFlow 2 that allows you to kind of port to different platforms. So if you're interested in training a model on one and then deploying it on another, for instance, if you wanted to take some sort of trained model, TensorDiffEq, and deploy it on an edge device, that's going to be the framework that'll kind of allow you to go through and do some optimizations for, if you want to put it on a Jetson Nano and you want to run it on that, it'll allow you to do some of those things. So it allows you to deploy in almost any environment. When it comes to the main things that we take advantage of for TensorDiffEq, mostly XLA optimizations, and then allowing AutoGraph to build out a graph for us instead of hard defining one. And that allows, so in TensorFlow 1, you had to build out how everything looked and was connected to each other. In this case, we allow the software to do that for us. And the result is what we believe would be way more efficient code that's a lot more readable to a user to allow them to interface with it. So that was our implementation, and that's how we've been kind of working with it. And so here, this is just a brief snippet, and we're actually going to work through this exact example in the live coding session. So this is just more to kind of describe the flow of how you would build out your problem, and then we'll get to the part where we actually do it here in just a second. So in order to actually interface with the code, it's a very simple example of Viscous-Burger's equation example. It's a very simple PDE. I should include on the slides. I'll put that in my notes for myself. It will be included in the slides when we look, or in the notebook when we look at it here in a second. So be able to kind of reference it there. But essentially, this is a one-dimensional with time problem, so X versus T. And the solution network, or the solution essentially looks like it starts as a sinusoidal wave, and then as time progresses, it becomes more of kind of like a sawtooth looking wave. So it starts as a sinusoid, and then it eventually kind of like rounds out to be this shock wave, basically, as time progresses. That is more or less horizontal and not nonlinear, kind of right in the center of the solution. So in order to build it out and actually solve it, first you will define a domain in terms of X and T. In this case, that's what we have. We do have a time variable. You don't have to have one. You can solve steady state problems if you need to. You just simply omit the time variable. And I'm not sure if my cursor is showing, so apologize if it's not. I'm kind of trying to point with it. So, so at the top here, time variable, you can define it if you need to. If you have a steady state problem, it's not required. Then you simply go in and domain.add, right? So you just add your different dimensions that you need. So you can do, in this case, it's just x versus t. So that's all we need, but you can add in here X, Y, Z, you know, whatever, or any type of, you know, if you're working in, you know, maybe some of the things we've been seeing recently, working with some of the problems in physics and some of the problems in nuclear engineering is, you know, we've got all sorts of different types of ways of representing the movement of an electron in three-dimensional space. And so you can have, you know, angles in here, you can have whatever, you know, you need to. You define the upper and lower bounds of that, and then you define the number of points. So that's the -1 and 1, and then you define the number of points that are on that boundary. Now, an important note about this is that these solvers are meshless, and the training that's being done is also not done on a mesh, which is a big divergence from a lot of traditional numerical methods that require you to essentially calculate, you know, the value of a solution network at a bunch of nodes across a structure or something to that effect. In this case, we don't do that. We define, in this case, it's a square boundary. The only reason we need to define the number of points along the boundaries is so that we can say that there's 256 points along this boundary for the package to do its calculations on. And then usually we'll subset that. You can or not if you don't want to. But you just need to define the number of points there so that you define the number of points that are being sampled. Inside of the domain, there is Latin hypercube sampled, meaning it's taking all different points, possible combinations of points in the domain. There's all sorts of different ones that can come out of that, in theoretically infinite. Obviously, we're dealing with computers here, so it will be finite, but down to, you know, whatever 13 or so decimal places. So the Latin hypercube sampling will go through and will sample inside of this domain you define. So in this case, I have an X limit of -1 to 1 and a T limit of 0 to 1. And then we're going to sample all of the points inside of that domain, which is exactly what this generate collocation points solve command does, is it will go in and sample inside of your two-dimensional window and grab all those possible different combinations of collocation points and then save those for later for using calculation. This is, like I said, done using Latin hypercube sampling. It is not necessarily random, but it is very good at distributing points across the entire domain. So once that is done, you kind of get into the meat of defining the problem that you want to solve. And in this case, we're defining we have an initial condition that is starting as a sine wave, kind of like I said earlier. So the initial condition is a negative, actually it's a negative sine wave, it's negative sine of pi x. Okay, so this is your initial condition that you will define here as a Python function. The cool thing about this is that any type of Python function you can conceive, you can put into here. It's like a Boolean function, for instance. So if you have above this value, it's this, so below this value, it's this. And I'm going to show a demo where we actually do that in TensorDiffEq, and you start off with like kind of a shock wave right at the beginning, at the initial condition. And you can do that because you can put in, just like I said, a Boolean function in Python, something that may be a little less or a little more difficult for some more traditional numerical solvers to solve a nonlinearity right on the initial condition. In this case, it's something that the solving with a neural network is actually pretty apt to doing, because it doesn't really care about continuity in the solution. It's a nonlinear function. It doesn't matter if the function that it's approximating is nonlinear. And so with that, you'll define an initial condition. So here we have this IC function. You will input the domain to that. You will input the initial condition. In this case, this is just the function, right? So we call this func IC, FUNC IC, and then we input that into here, and it expects a function there. So you just will define it as that and input just the name. You don't need to define, you know, func IC of X. It'll automatically do that whenever you define the fact that the variable you're interested in is X. So here you define, since this is an initial condition, it's not in terms of T because we know T is 0. So we just say func IC of X, and then we define this function in terms of X, and then we feed that in. In this case, to round out the problem, we have two Dirichlet boundary conditions on the upper and the lower part of the domain. Both of them are 0. So in this case, we're just kind of hard forcing the upper and the lower boundary conditions to be 0. And that's all these couple of lines are doing. So that rounds out our initial conditions as well as our boundary conditions on the problem that we're trying to solve. So once that,
Levi, there is a question in the chat.
Oops, sorry. Let me go back here. If I can get it to show, there we go. Chat. So the collocation points, okay, so Vardil asked how the collocation points are selected. So they're selected using Latin hypercube sampling, and that, you know, without going down into the weeds, is a methodology of ensuring that your entire domain is being more or less evenly sampled, right? So it's not random necessarily. There is an algorithm as to how the points are selected. In order to actually like answer that, I'd have to kind of go in and look at some literature. But Latin hypercube sampling, the sort of one-liner version of it is a way of evenly sampling the domains, the domain that you're, you know, kind of giving to the problem. If you were to do it randomly, there is a possibility that you oversample here and undersample here and this, that, the other. So if you look at a random distribution, 2D distribution of points, you'll see there's like pockets of points in there. And that's something that, while it is capable, just a second, I'll get to your question here, Stephen. While that is possible, it's still possible to solve. It just kind of helps to have the entire domain kind of evenly covered. Now on to Stephen's question. If you want to solve a PDE on a circle, do I have to use polar coordinates, or is it a good way to use a non-rectangular domain? So this is something, so we're going to kind of talk about how the domains are defined a little bit later. In this case, we can take that question a little bit more offline, because defining in polar coordinates is possibly a way of doing it, where you define like an R and a theta that could allow you to do something similar. I have not tested that, but in theory, yes, the code here could support that, as long as you call it R and you call it theta, and you define, you know, your upper and your lower bounds on R and on theta. You should be able to, in theory, use the exact same code that we're kind of showing here. Or I guess actually it should be the previous slide. There we go. So you would just define your, you know, you would have an R and a theta, and then you would be able to, you know, do it that way. Or theta and phi, I guess, if you're, you know, however you want to kind of define that. So yeah, so that should in theory be possible. I have not tested it on a particular problem, but if you have a problem in mind that you're interested in trying that on, get in touch with me, and I'd be more than happy to sit down and we can kind of work through it in the code. Okay, and that's true for anybody on this call, by the way. We're part of the Scientific Machine Learning Lab's very interested in working with different problems in different groups. We've got a lot of awesome different collaborations across the university at this point, and we are always looking for new problems to try and work on. So just feel free to get in touch with me after the seminar, or Dr. Tao, and we'd love to link up and kind of take a look at what problems you're working on and how you want to apply pins to whatever you're working on. Yeah.
Hi. Yeah. So I have a question. So the points that you mentioned in inside the domain.add, the 256 and the 100.
Yeah.
So just curious. So do they define the mesh size?
So in a way, yes, but inside the collocation, inside of the domain, it's important to note that there is no actual mesh. All you're doing is defining that 256 is saying that I want that level of granularity between -1 and 1 on the X domain, literally just on that line, or I guess on that upper and lower line, I guess, depending on how you're looking at it.
Got it. So yeah, if I increase that number, I'll have a much more accurate solution. Right.
Yeah, so depending on the problem, yes. So you can raise that number, you can add a lot more points between -1 to 1, and you should, yeah, hypothetically get a more accurate solution across the domain. You'll increase computational complexity, especially because in this case, whenever under the hood, whenever it generates the collocation points, or whenever it generates the boundary condition, like the solver, when it goes to solve it, it creates all the combinations of X and T. So if you were to scale this by a factor of 4, you have to keep in mind that you're actually scaling the number of boundary condition points by 4 squared, because you have a 2D domain. So it's just something to kind of keep in mind whenever, if you were to just, you know, double this number, you're actually multiplying the number of points that go into it by 4. So you'll start to slow down your compute costs. You'll increase computational cost when you do that. But yeah, that's kind of like a no duh sort of moment, right? You increase the number of points, takes more power. Right. So
yeah.
Okay. absolutely. Yeah, no problem. And we'll go through a live coding thing too, by the way. This is just intended to be an example, like a snapshot of how you go through it. And we'll go through specific examples too. So questions arise later, please feel free to chime in there too. So once these, the initial conditions and all the boundary conditions are defined, so here we have our initial condition, our Dirichlet BCs that define the upper and the lower values of the domain. I'm sorry if that was covering, by the way, I'm looking at the chat box here, so I'll get rid of that. So once you define all of that, you just put those into a list, and you can list as many of them as you need. So if you have more boundary conditions because you have more, you have a, let's say, an X and a Y and an initial condition that's in terms of X and Y, and you need to add, you know, 2 more Dirichlet boundary conditions on the upper and the lower Y domain, you just do that here, and you would just drop all of those into a list. So you would have an upper Y and a lower Y, and boom, now you have your 2-dimensional domain boundary conditions defined. Okay, so you would just, so picking up right at the BC list definition, so this is just kind of the second half of the code. Once you have that defined, you'll just go in and you'll define, I call it here F model. That's just generally the framework I use. Nothing really required that it's called that. Later in the model, you call it, whatever you've named it, you just will put down here. But I use F model just because it's, you know, generally kind of easy to remember. So this is kind of where the meat of defining your PDE comes from. And so you define it a little bit in TensorFlow syntax. Well, you define it in TensorFlow syntax, and then you kind of write it out mathematically as a formula, in, you know, to where it's essentially a strong form residual function where you have it equal to 0. So you need to get your PDE to a point where it's, you know, the second derivative of X times this, you know, plus the second derivative of Y in terms of Y times this equals 0. And then at that point, you can plug that in, and that is the output of your F model function. You have a residual function that is output from your F model function. Now, whenever you write it, so this is where kind of things get interesting, and why, you know, how the scientific machine learning and the actual neural network comes into play here. So what you're doing is you're using a neural network to approximate the solution. So that means that you need to define your PDE and its residuals in terms of that neural network. So what you do in this case, you will define, you'll pass in a U model function here. And that U model function, it's not required to be called that, but it makes things a little bit easier later on. All it needs to be done, you need to pass this in, and then all it does is go right here. Your U model is your neural network model. It's actually defined in the layer sizes that you have outlined here. At this point, to answer the question that's probably bubbling up, right now it's only fully connected layers, but we'll get into how to define custom neural networks later, and I'll show you some stuff in the docs of how to do that. So the U model is your neural network model. You'll pass it in as an argument, and then you'll call it here. So this could be just model, or it could be in net, or it could be whatever you want to call it. As long as you keep that framework consistent in this next line, it's fine. And then you'll pass in your variables that you're interested in this case, the number of dimensions in your domain, X and T. So this is where things get interesting. So you say that your U, we call U the neural network, right? We have U model, and then we have to concatenate those 2 inputs together, right? So that's all it's doing is stacking them basically as it feeds them into the model, because everything is vectorized in TensorFlow. So you just got to kind of keep the tf.concat syntax and then input your X and T. In this case, if you were to want to add another dimension, it'd be X, Y, and T, and then you would still leave the 1 because that's the dimension that it's concatenated on. But you would have X, Y, and T here, and your F model will be terms of X, Y, and T. So you define your U function, and this is how you define the PDE in TensorDiffEq, is you say U sub X, right? So we'll call that U sub X, and then you use this TF gradients function. You take the gradient of U, which is your neural network, with respect to the input X. That's all it is, and that gives you your first derivative. Second derivative, same thing, U sub X in terms of X. And that gives you your second derivative of X with, or the second derivative of U with respect to X. Same thing here. So if you look at the Burger's equation PDE, say something off of, I can't remember exactly offhand, but something to the effect of, you know, U sub T minus the second derivative times a constant equals to 0, and the plus or minus, something like that. We'll look at it in a later example. So, oh, it's actually, I'm sorry, it's right here in front of me. So it's U sub T equals U times U sub X, yeah, minus this constant here value times the second derivative of X. So I just forgot this term in here. So, all you need to do is define your derivatives define the derivatives in terms of u and stack those into an equation. And if you were to write this out as a PDE, you would have equals to 0 on this side, like equals 0, boom, done. That's your residual function. And then you return that. Now, when it optimizes, what it's trying to do is it wants to drive that residual to 0. And when it does that, it forces the neural network solution to constrain all of the physics that you've defined in this equation to be true as it's solving. So if it drives that residual to 0, then the function that comes out hypothetically must be the solution to your neural network, as long as all the residuals are driven to 0 and the boundary conditions are exactly accurate. Now, both of those things, because we're approximating using a neural network, may or may not be true, just because we're minimizing by a mean squared error in this case. So you'll have a little bit of error there as you approximate using the neural network, but in a lot of cases, it works pretty reasonably well to just use mean squared error and minimize with respect to that. And we'll talk a little bit later about maybe how to modify the minimization criteria. So as I said a little bit earlier, you define your layer sizes. In this case, we define, was this 1, 2, 3, 4 hidden layers. The input layer needs to be 2 because you have 2 input variables, x and t, right? And then the output is 1, which is just your u. In this case, you're just your one solution. Now, if you are doing something in, let's say you have you're solving the Schrodinger's equation and you have a real and an imaginary output, right, that you're trying to solve for. In this case, you would have this output layer be 2 because you have 2 different, a real and an imaginary component to your solution. But that's the unique thing about pins, is that it doesn't require a substantial rewiring of everything to change the number of inputs or the number of outputs. You would just change the number of neural network, the number of nodes, and as long as everything here marries up, boom, done, no problem. So in order to actually train, you'll call this model function collocation solver ND is the name of the collocation solver in TensorDiffEq. There is another model that we'll get into in the live coding session called the discovery model, which does some inverse modeling, parameter estimation. But you'll initialize the model using this call, and then all you have to do to train it is compile the model. So model.compile, and you'll feed in your layer sizes, your F model, which is just your neural network or your system of equations. Or equation in this case, the domain that you had defined earlier in terms of x and t, right? So that object that you built, and then the list of boundary conditions. So here we have the list of boundary conditions that we defined here, all of those different boundary conditions. As long as those are in a list, it'll iterate through the list, and the loss function will automatically be built to force all of those things to be true. It'll minimize all the residuals to 0. It'll make all of the Dirichlet boundary conditions, let's say, marry up to whatever value or function that you've defined in terms of that x, y, or whatever it is dimension. And then it'll also make sure that your initial conditions, if you've defined them, are also minimized with respect to what the value of that function should be at that particular x and t combination. So that all of that happens automatically under the hood when you call model.compile. It builds out the entire graph for you. So that's all done using TensorFlow 2. All that happens under the hood, and then you simply call model.fit, just like you would in scikit-learn or whatever other main kind of machine learning frameworks that you're probably familiar with at this point if you work in Python. You call model.fit, and then you'll say the number of TensorFlow iterations. In this case, the Atom optimizer is what's used. That can be modified, but the Atom optimizer comes first. In this case, we solve using 1,000 iterations of Atom. And then we go in and we fine tune the solution using LBFGS, a Newton solver, second order solver, and we do that for 1,000 iterations. And that will kind of get your, so this sort of 2-stage training model where you get close with Atom and then closer with LBFGS came out in one of the very first papers that really, at least for the PINS framework, that really kind of catapulted this into the spotlight. That was in a framework or a training methodology was used kind of as 2-stage methodology. And we've noticed that it pretty consistently does really well. There's some problems where it doesn't, but for the most part, it's a very good way of at least starting to get a solution going. Okay, so in this case, you'll call model.fit. You can push 0 here if you don't want to do any Atom and you only want LBFGS, or vice versa. So you just put in 0 iterations, or just leave it blank and it'll default to none. So yeah, so that will generate your solution. In this case, what you get is the solution network. And now this is kind of plotted. So we'll get into in the live coding part, like how you actually kind of get to this plot. But what you're looking at here is the 2-dimension X versus T domain. So this is kind of just everything, every, X like line, if you will, is drawn out vertically, and then kind of the colors are filled in between everything to make it look kind of like color coded and nice. So what you'll see here is coming up, you have a low value. So it starts off and it's negative 0.5, and then it goes up and it's positive 0.5. So it's kind of like a backwards representation of this, but you can see it sort of starts off as a sinusoid wave. And then gradually becomes this shock wave where you have this nonlinearity in the front, so that, or in the middle here. So that corresponds to this horizontal line, vertical line right here. So this is these plots are just basically snapshots, like cross sections of the domain as the solution evolves. And you can see from the legend down here that the blue is the exact solution, which is generated using a kind of a high fidelity solver, using a quadrature solver in this case. And then the prediction neural network is the dash line. You can see that it nails it. The solution is, in this case, you get down to, 1 to the -4th L2 error, right? So not residual, that's a pretty high residual, but that 1 to the -4 L2 error between a true solution that's calculated maybe using a high fidelity solver, such as Claw or whatever, and then compared to the pin solver, that L2 error is usually really, really, really low, especially for this. It's somewhat kind of, like I said, a hello world example. It's usually very reliable to solve. So one thing that's exclusive to TensorDiffEq, and this is something that we've developed in-house here at Texas A&M, is something called the self-adaptive solver, wherein you weight the loss function in different places. Each collocation point has an associated weight. Each initial condition point has an associated weight in the final solution, or in the training rather. So that residual is weighted by a certain amount, and as the training progresses, those weights are updated, and that causes the neural network to be able to really to more accurately approximate a solution, because the weights are driven by the volume of, or the volume of the residual. So if there's a high residual at a certain point, the weight will also increase, and it'll drive that residual down, is basically the premise of the self-adaptive solver. And here is an example of using it. We'll actually run through this example later, so you can see how to use it. This is the baseline pin solver. It is after training, believe it or not. So you can see here, as the last plot, everything, the exact solution is right on top of the prediction. In this case, it really fails to train. It fails to be able to approximate that solution accurately. However, using the self-adaptive solver, green lights, looking great, right? Everything looks good here. And so we'll use the self-adaptive solver in a second, and I'll show you how to kind of execute that. I'm going to move this along because I just realized that I'm 10 minutes over on this part of slides. So, all right. So in this case, so currently some of the supported stuff we just got into a little bit. We can solve, I say square, but if you were to define, like we talked about earlier, polar coordinates or something to that effect, you could absolutely do that. And we can talk about that offline. Boundary conditions, we mentioned Dirichlet, we mentioned Neumann, so for boundary conditions, we mentioned Dirichlet specifically. You can define a Dirichlet condition as a function, so as a function of X, or a function of, I guess, T in this case. Periodic boundary conditions, so if you're trying to solve maybe some materials informatics problems, or the Allen-Kahn problem that I just showed uses a periodic boundary condition. And then also Neumann boundary conditions. And the docs have a lot of that stuff on how to use that. Initial conditions, you can solve linear, nonlinear, you can find as a Boolean function, like whatever you can conceive for the most part will work. Asterisk, right? That's not always true, but I've been able to define most things that I wanted to using just a Python function as an initial condition. So single GPU baseline is self-adaptive solving, multi-GPU baseline solving. The self-adaptive solving gets a little weird if you try to distribute across multiple GPUs. Is something I'm still working on. You can transfer learn using this. So you train a model, and then you kind of capture it. You can save it using model.save, and then you can re-import it and use it later, fine tune the weights. You change just maybe a parameter in the model, and you don't really want to retrain the whole thing. You can just save the weights, and then you can just kind of fine tune it for your new parameter later on. So that's something pretty useful. Any loss function that's supported in Keras. So I defined mean squared error earlier, but you can do some other ones too. as well as any optimizer that's defined in Keras. I don't think I have that in here, but you can use, we use Atom, but you can use RMSProp or AdaGrad or any of those others that are in TensorFlow Keras. All of those optimizers are fair game. And now to be released here shortly, you can solve systems. A couple of PDEs are kind of automatically, if you define it correctly, you can use systems of equations. So having multiple residuals where you have multiple different things that you want to drive to be zero, and we'll look at an example here shortly of that. That'll be released in version 0.2. Right now we're on 0.1.9, and we're kind of putting all the final touches on releasing 0.2, which is going to include being able to support systems of equations. Currently, it can support coupled PDEs. If you can define, one PDE in terms of another PDE, you can do that in here already. So discovery model, this is something we hadn't talked about yet. It's inverse modeling, so you can learn parameters from data. So I'll show you an example of that. And then data assimilation, I'll have an example for the workshop yet, but being able to assimilate, like let's say you have a snapshot of the evolution at time t is equal to 0.5, because you sampled that data there, that you have that, so you want to assimilate that into your final solution. You can do that as well in the package. So I think with that, that's all I've got for this deck. So we'll go into the live coding here. Dr. Tal, do you want to go ahead and take a break? And then we can dig into that, maybe, I don't know, just a couple of minutes here. What do you think?
Yeah, sure. Like say 2:20, I think, I'm not sure, 40 minutes, do you think that's enough?
Yeah, I think that's fine. I had a couple of things that, yeah, that should be okay. Yeah, I'll just kind of burn along. I talked a lot more. I think I walked through a lot here that'll save me time later. So I think that should be fine.
Sure. Great.
Okay, sounds great. All right, we'll see you all here in just a minute. So 2:20, we'll resume.
Okay.
Okay. I got 220 on my end, so we'll pick it up here. So I'm seeing here, aside from initial conditions and boundary conditions in the Q&A, does the pin use any other data? So it does not for the forward solver. It doesn't have to. It can. It can. So I mentioned that there's some data assimilation that can happen, and we'll actually look at briefly an example of an area where you can take in, or a problem where you can take in a tracer in a, let's say a 2D flow around a cylinder problem, which we'll show. So you can take in a tracer, and then from the tracer, you can learn the pressure and the velocity that happens inside of that, inside of the wave, or the wind tunnel. So does it take in some sort of data? Yes, it takes in the tracer concentration, but what you get out of that is pressure and velocity data that otherwise you wouldn't be able to get. So that's a kind of a really unique application of pins, is being able to do not even, yes, inverse modeling where you can learn parameters from data, and we'll show one here shortly, but also ones where you can assimilate data in and learn, just like I said, from a tracer concentration, what the pressure and the velocity is that's happening inside of that wind vortex, inside of that wind tunnel. So, it does not require data to do forward problems. So the Berger's equation I just showed is the baseline example, doesn't require any data whatsoever, because you know the initial condition and the boundary condition, so that's an exact solution. You already have that. It's a sine wave or whatever. And then all you are doing inside the domain is forcing the residuals to be 0, which is a known value. So you don't need any other data to solve it. So you can, sorry, pin implementation compare in terms of the number of degrees of freedom with a high fidelity solver. So similar in nature to a high fidelity solver, you can modify the number of degrees of freedom. The fidelity of your solution is driven by that. So it's a parameter that you can choose. So you can choose a number of collocation points. You can choose the number of boundary condition points. And then at each one of those points, you're solving for a U function or a U and a V or a, whatever, real and imaginary. So all of those things are sort of synonymous. The only difference is that you're not actually solving on a mesh in this case. So each node point doesn't, have a grid location and then a, subsequent like solution value at that point. So the answer there is the two are sort of comparable in that you can select that number similar as you would to the fidelity of a mesh in a high fidelity solution. Yes, it's also true. Thanks, Dr. Tao. It doesn't have basis functions. That's correct. So there's no test functions. There's no anything like that. Your test function in this case is like a neural network, basically, that you're approximating to be 0, or to have a residual of 0. So yeah, so does that kind of answer your question about the number of degrees of freedom? In this case, the degrees of freedom really are a kind of a hyperparameter you can select, and it's just the number of points that you want to feed through the solver. And it'll learn at those points. Have weights. Oh, I see what you're saying. So you're talking about the number of parameters in the model. So that's also a parameter that you can select, so in the neural network, there are weights. That's correct. Each point does not require its own set of weights. So what you do is you have one solution network, one single set of weights that every x and t value you feed into it goes through that same set of weights, and then a value comes out on the other side. That is the value of your solution at that point. So the number of degrees of freedom is just the number of neural network weights in that context. I see what you're saying now. The number of degrees of freedom that you're training are just the number of neural network weights, and that can vary based on the neural network size. We've used anywhere from I think 5,000 to like 50,000, but each point, let's say each node point or each collocation point doesn't have its own associated set of weights. It's one set of weights that everything is fed through that will allow you to that creates the approximation.
Yeah, my take on this is something like this. There's no free lunch. Whenever you want to resolve some fine structures there, you need that number of data points to represent the fine structure internally of your solution space. But now with the traditional methods, you have a basis function. Those basis functions are very fundamental, primitive functions, might not be very expressive, not very expressive. You cannot easily construct arbitrary functions with a simple 2 or 3 of those basis functions, put them together. Probably need more of those. But for neural networks, all the functions you are using here, it's very, very impressive. That makes it probably, that's my understanding, that you will not need that many number of data points to represent your structure or your function. So I think it's related, but it's harder to think about direct connection between the number of weights and biases to the DOF, and but that's just my understanding. I don't know if there's any mathematical proof about how they are connected. There might be some connections, but it's just probably not that simple connection, depending on the basis functions of the traditional solver and also based on the neural network itself, the structure of the neural network itself.
Yes. Yeah. Exactly. So what you're training in this case isn't an expression at that one point in terms of degrees of freedom. It's an entire neural network that will then approximate every single point in your domain as you pass it through. So you still have degrees of freedom, just they're in a different place. and it's like Dr. Chow said, it's as expressive as you make it. So you can make it huge, you can make it small. Some problems work well with small, some problems don't. So it varies, and we'll look at different sizes through this too. So with that, so I'm going to start here and looking at the code, and we will. So first of all, this is Google Colab environment, and let me go ahead before I get kicked off here. I'm sorry, and send this link out to the chat so that everybody can hop on. So when you open it, it's probably, and you try to run it, it's probably going to tell you to save it as a new notebook. So you can do that. Go ahead, save it as a new notebook, and open it for yourself. Whenever you do that, it should default to it. So go over, first of all, hit file, save, save as, let's see here, save a copy in Drive, and it'll open in your, if you're on your TAMU email, it'll go ahead and open in your TAMU Drive. And then make sure to go into runtime. And so one of the cool things about Colab is you get free access to GPUs. So you can go down here and say, change runtime type, and make sure that the hardware accelerator, this little piece here, is lit up. It says GPUs. Otherwise, it'll say none if it's just on CPU, and you can also choose to do TPUs if you want to try with those. So I just usually stick to GPUs. That'll spool you up an instance on Google's servers. That's just, like I said, it's free. Typically, it will only let you run for an hour or so you can kind of dabble with it. You don't get free access to GPUs all day. They'll eventually kill your instance. You can upgrade to Google Pro, Colab Pro, which is what I've done just because I use it so often. And that gets you access to kind of like nicer GPUs, more RAM, and then like a longer runtime. It still is a space available thing, so they'll spool you up an instance basically on a place in their server that they're not doing anything right then, and they'll give you access to that GPU. So, so go ahead, take that notebook, copy it to your drive, open it up, and you should be able to go ahead and you should be able to click through it. So if you're not familiar with the Colab environment, you're not familiar with Jupyter Notebooks, to run a cell, you hit Shift Enter. So I'm going to go ahead and spool this and make sure that this is up. So I'm going to, first of all, check and see that I got a GPU instance. You can, the bang here, this bang command, this exclamation point, allows you to run a bash command inside of the server or inside of the Google Colab cell or the Jupyter Notebook cell. Even if you're working on Jupyter Notebooks, the same is also true. So you can run that and it'll spit out the kind of GPU that you have. So in this case, I've got a P100. So pretty good, nice GPU, Pascal architecture, and it's got 16 gigs of RAM. So that should be plenty for what we need to do. So the first thing that you need to do if you're going to run TensorDiffEq is install the package. You can do that using pip. So just pip install TensorDiffEq, once again using the bang command to install the package, because you have to do that on the command line. So you can just do that here using the bang. So I'm going to go ahead and run that, and it'll run through the install pretty quick usually. Yep, so there we go. So successfully installed DOE, which has the Latin hypercube sampling, PyFiglet, which does some of the visualizations we'll see later, and then TensorDiffEq, the package itself. So first of all, as with most Python scripts, you got to go ahead and do all the imports. So we're going to pull in math, which has a Py function in it that we're going to use later, SciPy, which allows you to import some data, TensorDiffEq, and then some of the subsequent pieces of it, boundaries, as well as models. So we'll run that, shift enter, and it'll import. So there we go, it's complete. So this is the exact same problem we just looked at. So at the risk of blowing past it again, the actual model that we were trying to solve earlier, the actual partial differential equation we're trying to solve, was just this simple, u sub t plus u sub x minus this constant times the second derivative is equal to 0. So in this case, it's Viscus-Burger's equation. You can have an Viscus-Burger's equation where this constant is basically 0 and there's no diffusion term. It's a little bit, well, we've come to find out a lot harder to solve using pins. We've had some recent experiments where you're trying to drive this term to 0. We're kind of working in that space. But this version of the Viscus-Burger's equation, where you have this diffusivity term here, is pretty easy to solve using pins. And so that's the one we've selected as this example. The initial condition, like I said earlier, is a sine wave, negative sine of pi x. And then the initial condition, or sorry, the boundary conditions, t and -1 is the same as t and +1, which is equal to 0. So the Dirichlet boundary conditions that we set in the previous code that's kind of just writing it out, so it's a little bit more straightforward to see. So with that, we'll define the domain. I'm not going to rehash all of what I said earlier. Once again, x and t, we have the same number here, and if you're interested in playing with that number now, you can. Feel free to change that, run it for yourself, and you can see. So I'll go ahead and run it with the same numbers, but you can up this value here, and you can kind of see what it does to the computational cost. Same thing with the number of t. If you want to increase that fidelity, you can do that there. So then we generate the collocation points inside of the domain. In this case, we'll just take 10,000. Once again, this is generated using Latin hypercube sampling. So it'll save all those points in this domain object. So we just got to run it. And then later on, we call it, and it'll pull all those out of there. Define the initial condition, which, like we said, is a negative sine of pi times x. So we kind of wrote that out up here. Scrolling up, so negative sine pi x, boom, we just define that as a function in Python in terms of x. So the input of that function is the x is just the variable. I just called it x to make it consistent. You could call it whatever you want. And then it returns the value of negative sine of x times pi. So, and then let's run that cell. So once you define the function, then you put it in the initial condition object, like we talked about earlier, func IC, and then you give it the variable x that it needs to feed in. So here we called it x to maintain consistency. In this case, we've done the same thing here. So this variable needs to match. The only thing is the alibi to that. Here it doesn't really matter too much. You can call it whatever you want and it wouldn't hurt anything. If you call it something different here in the initial condition and the upper and the lower boundary condition, if you were to call this, I don't know, something else, anything else, R, phi, or something like that, because you're dealing with a problem that maybe doesn't have X and Y, that's not a problem. The only stipulation to it is it's going to look for the same name that you gave it when you defined the domain. So I scrolled it up past it. So it's going to look for the same name that you gave that variable here, as well as here. So if you create a domain ND of phi and rho, or R and theta, let's say, and then you use X and T here, it's going to say, hey, what are you doing? It'll give you, Python will give you a bunch of errors because it won't be able to find that. Same thing down here. So you got to maintain that. That's the only point that has to be consistent. But inside of this function, you can kind of call that whatever you want. Why you would call it something different, I don't know, but you can if you want. All right, so then we'll define these all the initial conditions and the boundary conditions. We'll put those into a list as described so we can run through them. So the function model in this case is what we defined earlier, u sub t plus u sub x minus the diffusivity term. And we'll go ahead and we'll return that value, which we want to drive to be 0. So this is just a single equation. We'll define the layer sizes here. So this is defining the fully connected layer, or the fully connected neural network. In this case, we have 1, 2, 3, 4, 5 layers of 20 neurons each. And then that gives us, and this is kind of skipping ahead a little bit, but that gives us 1,700 degrees of freedom, 1,700 trainable parameters in the neural network model that are going to be subsequently, trained to minimize the residual and solve that PDE across all the X and T combinations that you feed into it, which is all the points, X and T points across the domain. So here's, like we talked about, initialize the model. In this case, we're using the collocation solver ND. We'll compile it, and we will just train, in this case, we'll train it for 2,000 iterations of just Atom. We don't need LBFGS in this case. This is a very simple problem to solve for the package. So we'll go ahead and we'll run it live, and you can see how quickly it goes. So it'll come up with this, the neural network architecture, little flashy logo, and then it'll train here. You get a progress bar. You can see on the GPU that I've got, which is P100, it's getting about 150 iterations per second. If this is going astronomically slow for you, check the runtime and make sure that you've turned it on a GPU. It should automatically do that because you copied the notebook, but if it hasn't, that's probably why. If you're not doing this on GPU, you maybe get 20 to 30 iterations a second or something like that. So the GPU makes this way faster, which is why I really like Colab, because you can do a lot of this and script a lot of this and do it on GPU for free. And then if you really are using it a lot, I've upgraded to Pro, and I've found it to be, it's like $10 a month, and I found it to be worth it. And then me and Dr. Braganetto, my advisor, will send emails and send invites to each other to the scripts that we build in Colab. So now you can do that whether or not you have Pro, but I've just found this to be a really good platform to develop on and to use this on TensorDiffEq on too. So a couple of admin things, all we're going to do. So now we have a solution, right? But we want to go ahead and compare. So how good is our solution? So we solved this in 17 seconds, but our loss is down to 1 to the -3rd. Now this is the aggregate loss across the entire domain. So this is not like a residual loss. Really, everybody who's from numerical methods is like, that's insanely high. This is across the entire domain. So it doesn't solve one time step first and then move to the next and then move to the next. So this is essentially, if you were to take the 100, I think, time steps and even this is kind of an oversimplification, but kind of divide this number by those 100 time steps a little bit closer to what the error would be at each individual time step. But even that's kind of an approximation because you got to break it down by vertical point too. You're also not on a mesh in this case. So you could basically just divide this by the number of collocation points, and that's going to give you a more accurate, like at that point, this is the average loss. So this is, yeah, like I said, this is the total loss. So we will go ahead and we'll download the data. So this is stored on my GitHub. This is the true solution because we want to compare it, right, and see how accurate we got. Kind of trying to burn through this quick because we've only got a few more minutes and I want to show a couple more examples. But we'll load that. So we called it Burger Shock. Boom. So that's the data that we wanted to compare it to. We'll go ahead and use SciPy to import that data, and then get that data parsed so that we can use it. And this is all copied, you know, if you copied this notebook, you can go ahead and kind of reference this later. So I'm not going to slow down too much to walk through this. But basically what this is going to do is model.predict is going to give you both the neural network predictions as well as the residual predictions as outputs. So this is the neural network at each X and T domain, and this is the residual. So like, you know, it should be close to 0, if you will, at each X and T point in the domain. Okay, and so we're gonna restructure that a little bit. So whenever you do that, you come in and you pull in the U prediction, and you can simply say, I want to do find L2 error, right, between the prediction and the U star, which is the actual U that we imported. So this is just kind of a flattened version of the exact solution that we pulled in. And then you can use this plot solution domain 1D, which is what what we showed earlier. And so there's some other helper lines in here, Tim kind of hitting the highlights so that we can kind of move it along. But so in this case, we'll just go ahead and we'll run it. And here we got down to 3.5% L2 error. You can get this a lot lower with more training iterations, but in the interest of time for the workshop, you know, if you push this up to 10,000, let's say, training iterations of Atom and another 10,000 of LVFGS, which still will probably take less than a minute to train, you can get this down to like 1 to the -4th-ish L2 errors. You can really drive this solution low. And as we talked earlier, this is just a solution domain with cross sections. So you can see, you know, X at each timestamp here, 0.25, 0.5, and 0.76. This is what your X value is and how well the exact solution hits the prediction. And you can see here too, kind of like the eyeball norm, right? This may be somewhat small. I actually kind of just thought about that, but the eyeball norm on this, if you just have a look at this solution, you see it's really, despite being, you know, having a pretty reasonably high L2 error, you're still really, really close here. So the standard batch size for training, in this case, it will default to the entire batch of, it'll default to, it'll do full batch by default, okay? If you want to modify that, which is encouraged because batch size, we've kind of seen a lot of instances where the batch size, making a smaller batch size and kind of doing mini batching and some stochastic gradient descent with mini batching, that helps tremendously in some problems. So in that case, if you want to do it, you'll just do batch size. Yep, there it is, batch size equals, and you can say maybe 200, right? And you already train it, and it'll do it with batch sizes of 200. Now that will slow it down because it's going to iterate through all 10,000 points. This is strictly for the collocation points, by the way. So each time you run that, it'll take 200 collocation points and then all of the initial and boundary condition points, and then just 200 collocation points. But it'll do that each time. So you'll really probably get you'll really get a good fit on your initial and boundary conditions, and then gradually you'll train your collocation points inside the domain. So that's a parameter I encourage you to play with. In this case, we did full batch, and that's generally the way we've defaulted to. But you don't absolutely don't have to do it that way. Does that answer your question, Stephen? All right, cool. Okay, so that's a Viscous-Burgers equation, pretty straightforward. I'm going to burn through one more that's a really simple 1D problem that's a little more recent and has kind of a little more functionality built out. So this is a very simple advection problem. So same kind of thing. So we're going to initialize it with a shock, and we're going to see the shock kind of move with time. And so this is something that pins do pretty well too. We've noticed just with kind of a simple advection, there, you know, as you scale this up to make it a little bit more difficult, like if you're doing Buckley Leverage or something like that, where you have like shock and other things that are in here, it gets a little tougher. But in this case, a 1D very simple advection problem is pretty good, and it solves pretty well. So you're going to go ahead and install the package, same sort of thing. Oh, excuse me, once again, before I do that, let me go ahead and send out this link so you guys can copy this. The other big part of this too is giving you all some starter code. So that's kind of my main objective with sending you guys these collab notebooks, is that way you've got something to like modify and build out. If you wanted to build out your own problem, you've got a place to start. You've got a little bit of a script, if you will, to do it. So I'm not going to run through like actually yeah, I'm not gonna actually train this one. I'll just kind of walk through it a little bit. So in this case, we actually do a high fidelity solution calculation in the notebook. So all of these are pretty quick. So in this case, this is done in just a few seconds. It'll generate the high fidelity solution using a kind of a known solver for advection. I forget the name of it offhand. Dr. Chow probably knows, but in this case, very similar setup, X versus T. The upper condition is L here. It's defined up at the top, X high. So L is 2, which is the channel length. Sorry, I just caught Sue's. Sue just asked if we want to do a 2 or 3 one, is it that we just need to add one variable Y? So let's go back to the burgers, and I'll show you real quick how one would do so. So we'll start here, and this is not a 2-dimensional problem, but I'll just kind of show you how that setup would look. So if you wanted to do that, you wanted to add an X and a Y, you would have to go in and you would do a Y here. You could just copy, let's say, the same line. You would still, assuming you want X, Y with T, right? So boom. So leave that, and you can go ahead and say Y. We'll call it 0 to 1. Oh my gosh. Call it 0 to -1 to 1 with 256 points. You would use the exact same collocation points function. You would need to redefine your initial condition, because now your initial condition would be in both X and Y. So if we just said that, and we could just grab this, boom, boom, and let's say I'm now just completely making this up, so it may or may not like actually work if you run it. And then for this, if we just go ahead and say that the upper and lower boundary conditions are the same, we just force those to be 0. We call that y, and then we would change upper x to upper y and lower y. And then we would just want to add in those same boundary conditions. Boom. Boom. Upper y. And I'm kind of winging this, so this may or may not actually work if I hit run. The other thing too, in this case, is you would need to have whatever interactions exist in your PDE model. You would just define it here. So if you were to have just, you know, a single use of y term, you would add this, oops, y, oh, sorry, kind of a significant deviation. So this, in this case, your function model will be x and y and t. And then here you would have x and y and t. So then you have your gradients, let's just call it that. And let's just say that you're gonna add, and this is not any sort of physical significance, so I'm just, you know, kind of demonstrating how you would do that. So there we go. So now we have that in there, and you would define your layer sizes. Oh, I didn't import any of this stuff. So you would kind of just go through, let's see. Oh, yeah, sorry. So yeah, so you would have a list here and you would need to add in your y. Boom. That should solve that problem. Yeah, there we go. So since your initial condition is now in terms of x and y, you also have to put in x and y here, right? Kind of like we talked about earlier. And then from there, you go your boundary conditions, your function model, and then your layer sizes, and then we'll see if this works. Yeah, so, oh, I didn't, that's because, like I said it earlier, but I didn't do it this time. You now have 3 input layers, 3 input nodes because you have X, Y, and Z. So that should start to train. Yep, there it goes. Now the solution to this is going to look, I have no idea, but that would be how you would modify it for an X, Y, and a T. And then you would have to run some other code down here to import a solution and then compare it. But that would be kind of a brief way of doing that, or a quick way of, you know, kind of how you go about adding another dimension. Same would hold true for Z. So if you wanted to add it. Yeah, no problem at all. That's kind of why we did the live coding. So that's, yeah. Good. All right, sweet. So I'm going to drive on with just a couple more examples in our last 15 or so minutes. So I can, mostly so I can get y'all, can't seem to access the second note. Oh, I need to make that public, actually. Apologize for that. That's on me, Steven. So I'll do that after the, save the link. I'll do that after the presentation. I'll make that public. That was my fault. Okay, so notebook 2, so the advection problem, let's go back to it real quick. I apologize for getting a little distracted there. I wanted to answer that question and show you how to do that. Okay, so the advection, so this is once again a simple 1D problem, and you start the shock in the center and you kind of watch it progress to the right. This is my right, I think it's left on camera, but if you watch it progress to the right as the solution evolves with respect to time. And so this demonstrates a few different things that I kind of wanted to show. One is how you would do a Boolean initial condition, because in this case you have a shock, and so you start off at 0.4 and then 4.0. So you have, and in the center at 0.5 is just a shock, or is a nonlinear, you know, initial condition. And so in order to do that, this is how you would define that Boolean condition. And in fact, I think I may be able to do this quickly so y'all can actually see it. I want to do, oops, to do this. So now go ahead and give it a shot, Stephen. Okay, cool. So this one has, this is how you would define a Boolean initial condition. So for all the values in X, which you feed in, it has to take it as a list, because otherwise it it doesn't vectorize it correctly. It's kind of odd. And this was a little bit of trial and error. So I had to go in and define this list, which I just called out. And then for the values in the X that it's fed in, if the value is greater than 1. So in this case, actually, I'm sorry, the trench is 0 to 2. So the halfway point is actually just at 1.0. So if it's greater than 1.0, you would say it's 0.4. If it's less than 1.0, you would say it's 4.0. And what that gives you is, I'll show you the initial condition here at the end. What that gives you is an initial condition that looks like this, right? So for the beginning, less than 1.0, and then 0.4 after that. And you'll see it's not dead on line. It's actually because this is at t is equal to 0.8. So it's a little bit past kind of the initial conditions. It's moved a little bit to the right already at t is equal to 0.8. So at t is equal to 0, at t is equal to 0, it starts off that, you know, this shock is right at 0.5, or it's right at 1.0. So if you go through and actually execute this, and I'm gonna have to kill the, I think the other instance, or is it gonna let me do it? It is gonna let me do it. Nice. Usually it doesn't let you run more than one notebook at a time. So Google doesn't like that. When you take up too much of their resources, they say, hey, don't do that. And you have to usually kill. So if you're trying to run, if you're running the other notebook and you try to run this one now, it'll probably make you kill the instance on the other. So I'm just going to go ahead and walk through this. So this generates the analytic solution. So that's complete. And then we'll define the domain. And I'm going to kind of type through this quickly. The initial conditions and the lower, the initial condition is just the function that we defined. The upper condition is 4.0. The lower condition, oh, sorry, correction, that's backwards. Upper condition is 0.4. Lower condition is 4.0, which is what we showed at the bottom. Boundary conditions, feed them into a list. Your function model in this case is just q sub t plus u, the function itself, times q sub x. So all of that is defined here, just using the TF gradient syntax, like we talked about earlier. And you build out your neural network, run that, build out your neural network. So we have, in this case, 8 neurons, or 8 hidden layers of 20 neurons each, boom. And then in this case, so then another thing that I wanted to show, aside from the Boolean initial condition, is that you can walk this the step size of your optimizer down by simply recalling, by overriding the optimizer using a new Atom optimizer with a different learning rate, and then just calling model.fit again.
How was your interview? It just doesn't respect me, man.
Manish, you're
no,
muted.
I was going for, he's attending a talk. That's just what he's attending a talk. Yeah. How was the interview? Okay.
Hey, Dr. Tao, can you mute?
Uh-huh. Uh-huh.
Dr. Tao.
Uh-huh. Okay. Yeah, you're closing by.
I can't.
Uh-huh.
Let's see here.
Okay. Uh-huh. Uh-huh.
Yeah.
You have an option to create something.
I can't do anything with them. See if Dr. Tao can mute everybody. Okay, so I'm gonna drive on. So if you call fit here, so you go ahead and you compile it the same way that you normally would, and you define your optimizer to be an Atom optimizer, 0.001. And then call model.fit, and it'll go ahead and train 1,000 iterations at this 0.001 step size. And then all you got to do is, so you've got that, you hit model.fit, right? And it runs for a little bit, 1,000. You can simply overwrite that optimizer with a new Atom optimizer of 0.0001 and just walk that step size down to get a more accurate solution. So this is something that actually will go pretty quick because this is a small problem. So if you just run that, it'll pull this up multiple times, because whenever time you run fit, it'll show this network summary. So it shows this multiple times. It's just the way it's written, something that I can kind of look at later. But you can see how fast that goes, 160 iterations. This is training it with 3 different step sizes that gradually, or 3 different learning rates that gradually decrease as it goes. And then, so that's done. So now we have a little helper function here that plots the slices, so you can kind of see what the solution actually looks like. And so in this case, you saw how fast that trained, and we get a pretty accurate solution here. We get some like Gibbs phenomena here at these at the points where it's like nonlinear. It's sort of an interesting thing that we're looking into. And Thanks, Dominic. I appreciate your help. Sorry, that's a DM. We can see here that it does actually get pretty accurate. I don't have yeah, we've muted the L2 calculation. So, but you can see kind of eyeball norm that it gets pretty close there. There's just no, there is a little bit of a Gibbs phenomena here, which is actually something we're kind of doing some research on how to remove. Okay, cool. So let's see. So let's go now to using the self-adaptive pin, which we talked about in the presentation. So that's another notebook to try out here. So this gives you access to a self-adaptive solver that we talked about in the slideshow earlier. In this case, like I said, each point collocation point is weighted by a certain amount, and the weights are proportional to, essentially directly proportional to the volume of to the value of the residual. So as the residual goes up, or if the residual is high, the weight will increase and it'll drive the residual lower in the final solution. And so that was something that we kind of wrote out here. We wrote a paper on it, and it's available on the website. So if you do pip install here, same as last time, and there's my too many sessions notification. So I'm going to go ahead and kill the ones that aren't. Let's see. So we'll kill this one and this one and see if that will work. So yeah, you guys may have already gotten that if you're working through this with me. All right. So we're installing. So here we'll define the same X and T domain. We'll just have a little bit higher on the X side. Yeah, was it Sundar? Yes, I can absolutely send that out. I'll send you the Google links out, or I'll get with Dr. Tao to send those out later on. So, okay. So do all our imports. It's actually the same as last time, right? Same thing, X and T, and then we'll generate the collocation points. So this one will go, this one's kind of like less broken out just because, you know, at this point we're kind of a little bit more familiar with the syntax and the flow. And here our initial condition is, X squared times cosine of pi X as defined up here, right? So initial condition X squared cosine pi X. This is our actual PDE, by the way. I kind of glossed over this again. So we have two constants in here, 0.001 and then 5. And then 5, which we'll get into here in a second, as to inverse modeling to capture those, like grab those out of there using data. So that's the next example, and that's probably the last one for today, just because we're running up against time. Okay, so we'll go through here and define our initial condition. Like I said, X squared cosine. So we're going to define a derivative model to be used in the periodic boundary condition. So this is a little bit different. The periodic boundary condition will ask you, so if you're going to do a periodic boundary condition, which is basically saying the upper part of this boundary is connected to the lower part of the boundary, and it allows that kind of a continuity to exist between the upper and the lower boundary, essentially kind of simulating like maybe a material that you have a little chunk of, but you assume to be homogeneous across the entire like material. So it's like, okay, I may not know what goes on past this, but I assume that it's the same as this side. So you build in that periodic boundary condition. So the derivative model, in this case, we just go down to the first derivative. So we say we have u and then u sub x, but we can actually say, well, I want the let's say I want the second derivative to also be continuous, the third derivative to also be continuous. So I could just go through and I can add this, and I can say, hey, keep going down and make all of the derivatives all the way down to the third derivative a continuous. Are you calling them, Dominic? All right, let's see.
Hello. Yeah, tell me.
All right. So yeah, so here we go. So if we wanted to drive it all the way down to 3 levels in the derivative.
Mine is muted. I disputed, no?
No, it's not. All right. So we can drive it all the way down to there, and you can add as many levels to this derivative as you want. And it'll return all of those, and it'll connect all of those derivatives with the upper and the lower boundary. Okay, so yeah, so you can do that. Now, in the interest of time, it's because every time you do that, you add a little bit more complexity to the calculations. So we'll go ahead and we'll just use the first derivative. Boom. Would it be a problem if the solution is not continuous? Not at all. So if for a periodic boundary condition, that's kind of like it's just the definition of the periodic boundary condition. So you're assuming that the upper is connected to the lower. But that's just the periodic boundary condition. So if the solution, and so I guess that is in regards to the solution, if the solution isn't continuous, I'm assuming you meaning there's like a break somewhere in the solution where it's maybe kind of going to a different like Boolean value, or it's going to a different value, and there's a kind of a jump or something like that in your solution. If that's the case, that's fine. You can still approximate it. It just may lose some accuracy. And I'm also seeing, so we are at 3 o'clock. So if somebody wants to jump off, that's fine. Or if anybody wants to jump off, that's fine. I'm going to drive on at least through this notebook, and I have one more that I'd like to show before we end it. And then we can, and I can get with Dr. Tao to send out the remainder of the notebooks, but that should cover the brunt of what I wanted to cover today. So, so if anybody needs to jump off, that's fine. Appreciate your time and attendance, and then we'll drive on for those that have a couple extra minutes. Okay, so as you define your derivative model, what is this? Akil, send me an email, bud, and we'll I'll give you some pointers. No problem. Yeah, this would definitely be above and over my head if I was in Math 152. I remember when I was in Math 152. So it's good times. All right, man. Yeah, send me an email. I'll be more than happy to connect with you and give you some advice. Okay, cool. I'll drop my email in the chat too, actually, now that I said that. Oops. Pick this back up here. So my email is just my name at Tamu. And I think that may be in some of my slides. So that's my email. So if anybody's interested in connecting with me after this to talk about this or anything else, just let me know and send me an email. All right, so back to the derivative model. So we can go down deeper if we want to, and as far as derivatives are concerned, we'll just go ahead and stick with the first derivative for now as a condition of continuity. So we have the initial condition. We've defined the function here, x squared cosine of pi x. And then we once again define that in terms of x. We have our periodic boundary condition, so we don't need an upper and a lower this time because we know the upper and the lower are connected, so we only need to define it one way, or we only need to define it once. Yeah, and then our VCs we'll put into a list here. So we have the initial condition and the periodic condition. Yeah, so we'll run that. Boom. All right, now for our function model, so we defined it earlier in terms of, so we got some second derivative with respect to x. So we have a second order PDE here. We have worked a little bit with the Cahn-Hilliard equation. It's just a fourth order PDE. It is still possible, and it actually works pretty well. So you can go all the way up to there using a periodic boundary condition and all of that to being true. So we would just simply write out the equation in terms of all of its derivatives as we've been doing. And this is the equation that we saw at the top. I tried, this is just kind of an admin note. I have here u times u times u instead of u cubed. That seems to work a little bit better. It's like more stable. It's kind of odd if you do throw like a u, caret 3, you would think that it would work, but something with TensorFlow syntax. You can use tf.power. But you can also just go ahead and use the star command, and when you do that in TensorFlow, it automatically realizes that you want to multiply those together. So if you use u caret 3, TensorFlow may not at least when I tried it last, TensorFlow didn't recognize that I wanted to cube u. It was like kind of a weird syntax thing. So this was a little bit more stable. So it's just kind of like an admin note if you're building something like this out. So we defined a residual function, Once again, that equal, you know, we would have kind of a little, you know, if you were writing out the PDE, it would be equal to 0 over here. Now, in this case, to do the self-adaptive solver, you need to define your collocation weight initialization and your initial condition weight initialization. All right, so these are a few more trainable parameters. In this case, you have this exact same number of collocation weights as you do collocation points, and you have the same number of initial condition weights as you do initial condition points. So you could change this to be N0 or whatever if you had, you know, that defined as a variable. In this case, I just kept it at 512 because that's the number of points. 512 initial condition weights because I have, if I scroll back up here, 512 in initial condition, or sorry, 512, yeah, initial condition points, which is the dimensionality of my X domain, right? Okay. Oops, scroll past it. There we go. So yeah, so I go ahead and initialize those vectors to be tf.variables. This is kind of some syntax that you just have to start with. Luckily, you don't really have to change too much. These weights are initially set to be uniform random, so between 0 and 1. So it just samples randomly just to get them off the ground. In this case, we've noticed that on the initial condition, specifically for the Allen column, this is also kind of supported in some recent literature in the pin space, is that if you more heavily weight, especially in advection diffusion or problems that have really kind of anti-diffusion term associated, that weighting the initial condition heavier seems to help quite a bit. So that's what we've done here. We've just basically said, all right, take that random uniform and multiply it by 100. So now instead of 0 to 1, I have 0 to 100 randomly uniform weights, or I'm sorry, randomly distributed weights. And we'll define our neural network model. So we have 4 by 128 fully connected layers. Initialize the collocation solver. Compile it. In this case, we want to say is adaptive true. So we've got the same stuff here. Is adaptive is true. You got the collocation weights and you point to the collocation weight vector that you created. Boom. Same thing with the U weights. U weights is equal to the U weights that you initialized here. Boom. Yep. And then you will call model.fit and you'll have the exact same syntax there. So this is going to take, so this is 10,000 iterations of Atom and 1,000 iterations of LBFGS. And this takes about 3 minutes or so. So while this is running, so let's start it. Boom. And then while this is going, we're going to run over to the docs. Yep. So this is going to take, yep, a couple of minutes. So while we're waiting on that, I'm going to send you a link to the TensorDiffEq documentation website. And this is where a lot of this stuff is written out. Basically, exactly what we're running through is broken down by kind of major, you know, there's a flow, define the bound, you know, define the domain, define an initial condition, define a boundary condition. So this is broken down kind of in the flow that we've been following, just so you can kind of go through and define your own problem. So it goes all the way from installing to generating a domain, which you talked about. There's a little bit more information here on how to actually use it, how to initialize things, a couple of examples, generation of collocation points. If you wanted to add more dimensions, we kind of showed you how to do that. It's also written about in here. If you wanted to define some of your initial condition and you wanted to do a Boolean, this is in here. I need to actually fix this because some syntax changed there, but that's just something to admin note for me. Instantiate the class, you know, boundary conditions, then building out the physics and kind of defining your model. A lot of the stuff that we've covered already, that is all kind of covered in here with just a little bit more content, a little bit more explanation. The collocation solver and how to actually use it, as well as all the different things that you can do with it. Like we talked about, I'm sorry, for the fit function, we talked about batch size, but you can also add in here a function mask, which I'm not going to get into. It's in our paper. I'm not going to get into for this talk. And then you can also distribute the solving. So this is where you would go through and say, hey, I want to distribute across multiple GPUs, and then it would do that for you automatically, assuming you have multiple GPUs available to use. And that's so really the only difference, which is kind of, I think, pretty cool, the only thing to push this across from a single GPU to multiple GPUs is enabling this single Boolean flag. You don't need to change anything else about your code. Everything else happens under the hood of TensorDiffEq. And that was the way I wanted it to be. And then your fit function here. So there's two different types of Newton trainers too. So there's a graph mode and an eager mode. I by default use the eager mode. There's another type in here basically is the bottom line, and you can try it as well. So if something is weird with your Newton training, if your LBFGS, if you're using it and it goes and he starts throwing nans and it's like it falls apart, you could try to change this flag from Newton eager to be true. You can change this Newton eager is equal to false, and that will use a graph mode LBFGS implementation that is a little bit more, in some instances, more stable. Okay. So then pin the collocation solver example. So this is a full script of how you would solve. I think this is the burgers. Yep. So you can create a full script here. The self-adaptive, which is the one we're working through now. So all of this is all written out here too, as well as in the books, or as well as in the notebooks. And then we're going to get into the discovery model. That's here too. Solving problems in GPUs. There's some considerations here. The hacking section is really what I wanted to kind of highlight here. So you can do custom neural network architectures. So if you wanted to go through and using the Keras API, you can go through and define custom neural networks. This would be how you would do it. So let's say I wanted to add batch normalization as an example. So when you start it, when you initialize it, it uses a vanilla MLP, fully connected layers. If you wanted to add some flair to that, if you wanted to do something a little bit different, the only strict requirement is that the input layer and the output layer are, the input layer is the number of dimensions of your problem, X and T in this case, right? So that's a 2. Then the output is 1, which is U, and that's what you're trying to approximate. As long as that marries up with this and with your domains that you've input, as long as all that marries up, then you could put like convolutional layers in here. You could do all sorts of crazy stuff if you wanted to. If you're doing that, would love to hear more about it or if you have an idea there, would love to hear more about it because that's kind of an interesting, way of thinking about the problem. Using some RNN stuff in here and kind of parameters that change with respect to time is another question. It's not going to be as simple as changing this, but that's something that we can chat about if you're curious about. But yeah, so this would be a way of defining a custom neural network architecture. If you wanted to change the activation functions, let's say it defaults to tan-H, you could change this to rel-U or whatever. You can do that here. You can change the initialization, and we use Glorant normal for as out of the box, but you can change the initialization to be something else if you want to. So all of that's possible by just simply defining this, and then whenever you compile, so you run the model.compile and you overwrite the default neural network with the one that you just defined. So you say model.u model is equal to, we call it model BN, model batch norm. So we just added batch norm here. And that's all we want to do is overwrite it, and then we just call model.fit, same as before. Boom, done. And then you can change the optimizers too. We talked about this a little bit with the optimizer and the learning rate dropping. So if you want to drop your learning rate, we kind of went over this before, but you can just say, instead of Atom, optimizers.sgd, and then you would just call model.fit. So you just need to overwrite this tf.optimizer object with a new optimizer, in this case an SGD one. If you don't do this and you remove that line entirely, it'll use Atom out of the box by default. Yeah, so here it's just using Atom, same as before, to overwrite and give it a different value for learning rate. It defaults to 0.005, by the way, which is important to note. So if you want to change that to make it bigger or smaller, you'll have to overwrite the whole optimizer using this syntax. Okay, so that's that. So let's go back to our code. It's probably done by now. A couple more minutes there. Boom, done. Okay, so the LBFG or the Atom trained in minute 45, and then the LBFGS trained in a minute and 3. So now we're going to go ahead and import the data like we did last time. I have this hosted on my GitHub. This is the true solution so that we can compare the approximated solution from the pin to the solution that we know to be true. I think from a quad or this solution I think came from Phoenix, and then that's going to allow you to go through and just plot same as before. So here we get 7.8% L2 error. So not too bad, but also not too great. So it's going through this plotting process here. There we go. So we can see, and this is just because we didn't train it for as long as it, so in the paper we show some results where this little bit of error is removed. If you let it train for a little bit longer, it'll get to that point. Just for the interest of having something quick for the workshop, we didn't, you know, if you up the number of LBFGS iterations that we ran here from 1,000 to 10,000, you'll get that error down to 1 to 2%, and the eyeball norm of this is substantially better if you do that. And those results are demonstrated in the paper. Yeah. And the other thing too is there's a link to the paper on the self-adaptive pin on the TensorDiffEq.io website. So this is the paper I'm referring to. So you can feel free to have a read with that when you get a shot. So back to the code. So the last one I want to run through really quickly before Dr. Tao moves me off the stage is a quick parameter estimation problem. Mostly I'm gonna share this notebook with y'all. And this is how, so if we wanted to learn this value, we didn't know what the value of, you know, we didn't know that this constant was 0.0001. We didn't know that this constant was 5, right? If we wanted to learn that from the data, that's something that TensorDiffEq also supports. So in a similar fashion, import the package. Import the discovery model is the one we're going to use this time. Instead of the collocation solver ND, everything else is the same. Just import that. You have to initialize the parameters. In this case, I initialize them to be 0, but you know, you can kind of experiment with that a little bit. So the parameters are going to be fed in as a list. So in this case, I know I want to approximate 2 parameters in the model. So I'll create two tf.variables, 1, 2, and put them into a list. So I'd create a tf.variable 0 and 0. So this is just a single value. There's no vectorization here. It's just a list of TensorFlow variables. And then from there, I take it and I actually feed. So this is this is kind of a syntax. This is a syntax requirement. This is a syntax requirement, is that you run umodel in here first, and then you run var, right? That must be the second input. And then after that, you have x and t. So as long as you follow this little template, if you're going to do this, this will work. So umodel first, and then the vars, and then x and t. So you define, in this case, we're doing the same Alan-Kahn problem we were last time. So it had the same setup, right? ut minus 0.001 u sub double x plus 5 u cubed minus 5u is equal to 0. Same setup, x squared cosine of pi x, which is actually interesting. You don't need the initial condition or the boundary condition in this case, but that's just where the data came from. So that's kind of something to note. The only thing required for this is the physics of the model and the data. And then from there, it'll be able to learn those parameters with a single snapshot of data. So in the syntax, whenever you define it, so we have var here, the first value of var, so here I called it params, it doesn't matter as long as you feed it in there correctly. As long as they'll take that first value, which is this number here. So C1 is var 0, C2 is var 1, right? So it's just a list. And then I say ut minus, yeah, this t var value here. Actually, I think that is a typo. So yeah, so that should be a typo. So that should be t var. This should be C1. I don't know why that's that way. That's weird. So I'll fix that. There we go. So that should be C1 times u double x plus C2 times u cubed minus C2 times u. So that's exactly what we had up top, where C1 should be 0.0001 and C2 should be 5. So we define that model, shift enter, and then we'll import the data, which is the same data that we showed last time as the comparison to get the L2 error. But in this case, instead of showing it as a comparison to get the L2 error, instead of solving a forward problem, now we're going to solve a problem where we're saying, okay, this is now my data that I want to be able to learn those parameters from. Okay, so we don't give it any hints except the physics of the model. And note also that this is one evolution. So we don't need multiple samples of this. We have one evolution with respect to time of this particular system. We have one experiment that we've run. We know the value of X across all the values of T, so we can just import that data. So this is just kind of modifying it a little bit such that we have it in a ready to use and get it in a fashion that TensorDiffEq expects it. We pull in data, we load the ac.mat file, and then we modify it a little bit, grab the actual data out of there, the actual solution data. And then what we need to do is generate all possible combinations of X and T. If you are doing a three-dimensional problem, X, Y, and T, or sorry, a three-dimensional problem, 2D with time, there we go. You would have X, Y, and T. You need to go through and define and use a multi-mesh function to create all possible combinations of X, Y, and T to do something similar to this. Flatten those out, make them into a vector, and then append those to a list to run into model.fit. This, we're not going to use collocation weights. You can do the self-adaptive training here. That's supported, but do you really want to weight data? You know, it's kind of a meta question. You weight data, you'll overfit. So do you really want to do that? You can, and if it doesn't work, then it may be worth trying. But there's kind of a big question or a meta question about weighting data in your model and your solution. So from there, our model, like we have been importing the collocation solver in D, but in this case, we'll import the discovery model. All right, and then we'll compile it similar to last time, but a little bit different of a compile function for the discovery model. We import the layer sizes. This is the neural network that's approximating the solution. The function model that we defined, the function model that was defined, and then we have all of the input values X and T. This could be X, Y, and T, whatever. We feed those in. We feed in the exact solution. So this is like the actual, sorry, not the exact solution. We feed in the data, in this case, the data. And then we have our params that we defined earlier. So the params were defined up here, and this was this list of 2 numbers, basically, that we want to show. All right. So run that. And then here I was just kind of demonstrating that if we run model.compile, if you want to change the optimizer, like we talked about last time or just a second ago in the docs, you can do so. In this case, we just changed it. So actually, we didn't really even change it from default. We just overrode it with this new one. Oh, we changed it. I see the beta parameter. I think it defaults to 0.99. So we just changed one of the momentum parameters to be 0.95. Not a substantial change, more so to demonstrate the capability. And then in this case, you just hit model.fit and you'll train that data. And it'll run. So this takes a little bit, and as it progresses, as it trains, so you can see here, this takes, so this even on GPU is going to take somewhere in the neighborhood of 12 minutes. The final solution to that, and I shouldn't have run it because I usually just kind of show that there, but it gets to be like, so the parameters we're looking for is 1 to the negative 4th, and then 5.0, and it gets down, it's like 1.2 to the negative 4th, and then 4.93 or something like that was the last value that it gets. So it gets down pretty accurate for this particular case. And so if you copied this notebook, you can see probably those values as long as you haven't run that cell for yourself. You can see what those values were prior to me starting it here, and then it just takes a little while to train, so it's going to run through that. And so with that, I think I'm going to do one last, or just show one last thing here, and then we'll call it a day for those that are still in. This is the Scientific Machine Learning website, TAMIDS SciML. And we have a couple of other demos on here, one of them being this flow around a cylinder problem, which is an extremely interesting application of physics-informed neural networks. I was kind of talking about it earlier, where we only had the tracer concentration data. But from that data, we were able to learn the horizontal velocity, the vertical velocity, and the pressure. And so it kind of demonstrated this nice little video. The only data that we actually had was this tracer concentration, but because we have, the Navier-Stokes equations in 2 dimensions, we can actually go through and based on that tracer concentration, figure out what the horizontal vertical velocity and pressure is. And so we have a few other demos on here. So this is the viscous burgers. This one is rather interesting. So this is a public Google collaboratory notebook, so you can go in and you can see it. All this does is import network weights from a repo that I have. If you actually want to see the script, and I'm saying this more for the people that are doing like research in this space, if you want a low level, not TensorDiffEq, but a low level starting script to be able to do some of this stuff, this is a good starting point, because this actually goes through, and it kind of demonstrates, this is how you would write out a system of equations in TensorDiffEq as well, where you had, maybe instead of one output, you could have up to, in this case, 5, or you can go up to as many as you need to. But it also goes through and like defines the loss function, defines the gradient, how to take the gradients, what is happening under the hood of fit, everything else. So if you're doing kind of research and you want to build your own version of this, or you have a very specific problem you're trying to solve, this could potentially be a starting point for some scripts. And then it also goes through and I think has some how to generate, it also generates a video and some other stuff too. But really the part of interest probably for people that are doing research in this is the component of like building out the model.fit piece. So with that, I think I'm good. Dr. Tao, I know I ran way over, so appreciate those of you that hung around for hanging in with me. I have another meeting at 3:30, unfortunately, so I can take probably a quick question or two, and then I'm gonna need to run as well, but I'd be more than willing to respond by email if you're interested in setting a meeting with me or anybody else. My advisor, Dr. Tao, just get in touch with us, and we're working a lot on the scientific machine learning front, so we would love to have a chat if anybody has any specific questions. And with that, I'll open the floor.
Hi, I just had a quick question.
Yeah.
Yeah, so I don't have a much background in neural networks. I have a slight background in machine learning. So question is, so when we say a layer in neural network, so what do we mean by a layer and what does it do?
So the layer in this case, and so for a deep neural network, a layer is just it's actually a linear combination of weights and a value inside of that layer. And so whenever you layer these things together, you're able to more effectively approximate like increasingly complex functions. So the layer in this case is just, and I know Dr. Tao, you had some good slides on this, and I may have been able to pull that up. I just want to see a diagram. So the layers are these, in this case, vertical components where it's just showing, you have multiple layers that can go in to make these deep neural networks that allow you to approximate more complex functions. So that's really where the layer thing kind of comes from. Being able to layer these allows you to just make things more, allow you to capture more complex dynamics.
Okay, so if I understood it correctly, so we have this input, and based on the linear combination of input, we get the first layer. Yeah. Now, based on the linear combination of first layer, we get the second layer.
Correct. And it goes all the way to the That's
okay.
Correct. That is correct. Yep.
So ith layer is linear combination of I minus 1th input or layer.
Yep, exactly. And that goes all the way back to the input layer. Yes, your final layer starts here and you just backpropagate, or not backpropagate, but you go all the way back through. And then in order to train it, you have to backpropagate the weights all the way back through it. And then each one of those are updated by a gradient descent. Each one of those network weights are.
The only thing you just missed here is the activation function. When you're going from one layer to the next layer, you need to use the activation function to give you some linearity. Otherwise, all the linear combination won't be able to get you anywhere. You need an activation function to construct this complex mathematical structure to help you to do the mapping from your input to your output. Yeah, so picture a kind of a layer inside of this is also an activation function like ReLU or sine or a tan a hyperbolic tangent that is kind of, you have the AX plus B, and then you wrap that around your your activation function goes around that. And then that's what's actually projected into the following layer. And then it does it again.
So it does AX plus B and then activation function and then projects that to the next layer and it goes all the way through to the end.
Right.
Oh, okay, yeah, understood. Thank you.
Yeah, no problem. Absolutely. If anybody else has more specific questions, like I said, I got to hop off. I would be more than happy to respond to any emails if there's any further questions. Appreciate y'all sticking around to the end. Anybody else, please let me know.
Oh, okay. Wait. So on that page with the artificial neural network, the IBM page, so it's mentioning the threshold. So if something's over the threshold, then it propagates to the next one. Basically, I just wanted to make sure I got this. So the activation functions like TANH and stuff, those are like continuous threshold, right? So that's like replacing a heavy side like on-off criterion with something that varies slowly from like 0 to 1. So it's not quite discarding something if it's below the threshold, but it's like modulating it somehow with that nonlinear function. Like, is that what's happening, or is
Yes.
that?
Yes,
Oh.
that's a way to describe it. Absolutely. So it doesn't, it can threshold if that's what you're interested in. But typically those functions are something like a hyperbolic tangent. And the shape of that is just kind of allows you to add in, you know, it allows you to just add in some of these nonlinear. So if it comes in and it's, you know, out here. So however, there's some issues. If you're way out here, you know, you'll have some issues in the gradients, but it basically allows you to build in a, and prevent you from getting way too far out of bounds and really over hyperstimulating certain neurons versus other neurons. So the other addition or the other additional kind of like, you know, like added benefit to this is that you kind of keep things within a certain confines, so it allows them to be more trainable, but you're not necessarily losing information.
Oh, okay, great. Well, yeah, I'll let you get to your next meeting, but yeah, thanks so much for this presentation. Like, very helpful, very interesting.
Absolutely, absolutely, I appreciate that. And please, yeah, email me if you have any further questions too.
Oh, okay, definitely.
All right, thanks, Tommy. Appreciate it.
Have a good one.
Thanks, you too.
Sure. Bye-bye.
Bye.